I also start with the concept of the aspect of spectral graph theory, some aspect of spectral graph theory, the problem session. I was introduced into this field by a supervisor, Stefan Wagner, and I seems to be loving this field for now. And I'm doing a lot of some of this research also in this field, right? So I think maybe 20 minutes and 15 minutes is enough for most of you to maybe go through the problems and I'll find and have a solution to some of these problems going to be discussed. Basically, I will not provide not all the proofs to some of the problems. Most of them will be an idea. So, and also, of course, there are also elegant ways to also prove some of these theorems. So you can just have to think about those problems and also work with that. Okay, thank you. So let's start with some outline. So basically, we will just, the idea is to maybe introduce to some of the problems where the research questions we could ask in most of these areas in spectral graph theory, and give an example as a form of a problem. Yeah, for us to just to see how such questions can be answered and some tools which mostly people use in solving some of this. So we start with the spectrum of course, we would like to know more about some graphs. Then we would like to know how to compute their spectrum. And also, I will also talk about we will also discuss some problems related to some spectral-based invariants. Stefan talked a lot about energy, and now will be maybe introduce some problems also in the spectral radius. Then our last thing will be so it's more of spectral radius now. So we talk about some bounds on the spectral radius and also some extrema problems also on the spectral radius, right? So let's start with our problem one, right? So as indicated in Stefan's talk, so we have some classes of graphs, and the natural question is we want to study the spectrum of these graphs. The idea is how do the spectrum looks like and how do we compute them? Do we have some relationship with some of these matrices, and how do we compute those spectrum? So I think our first problem is concerned with that. So we would like to compute this for the complete bipartite graph. And we would like to compute spectrums. When you mean by spectrum, when you talk about a spectrum, then you are referring to the adjacency matrix. And if you talk about a Laplacian, we are referring to the Laplacian matrix and the spectrum of this Laplacian matrix. So basically, what I'll do is we will explore two methods, right? The first method, which is also normally used, sometimes some of these matrices are or some classes of graphs are very easy to understand, and we can also do some easy calculations on them in order to obtain their spectrum. Some of them are also quite difficult, so we normally employ other methods. So I just introduce only two of such methods, which are quite simple and also interesting. So we will first start with what's the format of how the adjacency matrix of a complete bipartite looks like. So it's in this form. If you can rearrange the order of the vertices in such a way that we can have it in this form where this matrix O has all entries to be 0, and also this block. So it's this block matrix form where the C here has all ones. Yeah, and basically, for example, so let's take for example this is a complete bipartite. So we have 2, 3, right? So in this parted set, we have 1, 2 vertices, and we also have another 3 vertices here. So we can clearly say we have the C here and this transpose here, and the matrix orange. So by how we have labeled them, if you rearrange the labeling, it could also give a different structure, but all of it is, yeah, since there's a permutation method that can bring it back to this format, the spectrum are the same. So we can have this structure. And by looking at this form, the first idea that comes, how can I compute the spectrum of this matrix? And it's quite easier because now, if you look straight and look at this matrix, we find out that it has rank 2. So that means it has, so the number of, first, the number of edges of this graph is just n plus n. That's the number of n plus n here. So, and if I have rank 2, that means we have about the dimension of this null space is as n plus 2 minus n, right? So then with that idea, then we know that 0 is an eigenvalue and it has multiplicity of n plus n minus 2. So we find that most of the eigenvalues are zeros. Then we are left with 2 more eigenvalues to compute. So how do you compute them? So to compute this remaining eigenvector, we will try to go and look at the eigenvalues. We first consider the eigenvectors and defining in such a way that can help us. So that's another method people mostly employ. So we split already, it's already split into 2. This for our vertex set. And so for every vertex here, we take a vector here, a vector x here, and for every entry of this, it is assigned to the vector set, right? So if you are in this set V1, then we assign S1 to you. And if you are in V2, we assign S2 to you. So that's another way, a simple way of doing this. And we need to check whether this vector we have here is an eigenvector, right? So for it to be an eigenvector, then it must satisfy this condition, right? This equation. And if you from this equation, we can now derive these two relations, right? Because we have x1 here to these two relations, and if you solve this, well, you arrive at that lambda is equal to the square root of mn, right? Yeah. So these are the plus or minus. Oh, sorry, I think this did not show well. There's not enough space here, too much space here. So it is plus or minus square root of m times n. So now you have this whole spectrum of the adjacency matrix corresponding to the complete bipartite. Yeah, so we have, so that's one way of computing. Sometimes it's quite easy, as you can see from for the matrix, and we can do this analysis and easy analysis, and we can get back to this one. So that becomes our results now. So we have the spectrum of the complete bipartite has zeros with multiplicity n plus n minus 2, and we have square root of this. Basically, we can employ the same method or similar methods. For example, so if you have the spectrum, so with this one, so if you have knowledge of, you don't need to maybe compute the whole thing, knowledge of just only the pi-test set, the number of vertices in each set, you can easily say everything about the spectrum, and that's nice. Yeah, so you have 0, and by this 2 times 3, you have all the solutions. There's a spectrum given to you easily. Basically, we can also employ the same method or similar method and to compute the Laplacian spectrum. But maybe I'll leave you at an exercise, but I will prove these results later using the other method, right? And to introduce the other method, we will first have to solve problem 2, and that will help us to get enough ways also to solve this problem. Yeah. And problem 2 deals with some graph operations, and there's also another interesting aspect of this of how to compute the spectrum of some specific types of graphs. Um, so the problem is that if you have these as the eigenvalues of the Laplacian matrix, and as Stefan mentioned, and if you recall, 0 is always the eigenvalue, and the rest are positive values, right? Real numbers. So it turns out that the complements of this graph consist of these elements in the spectrum. These numbers in this spectrum, they're not real numbers in this spectrum in this form. So n minus where n is the order of the graph G. So what is the complement actually? So the complement means, so we have the graph and all vertices are connected, and most of the vertices are connected. So in this case, you create another matrix. This complement is just all those who are connected will no more be connected, and those who are not connected will be connected. Basically, that's the idea, the main idea of the complement. And it's to we'll first prove the theorem, and we'll use it to apply to solve our problem one. So the proof lies in, so let's start with this condition. So if you have the complement of a graph, right, it's not difficult to realize that if you take the Laplacian, right, and the Laplacian of the complement, there are some, because in this case here, some of them were not having edges, right, and those ones were having the ones here, right. So here there's not enough -1, and it's filled out by this side. So that's the consequence of the J matrix, which is a matrix with all ones, right? And to compensate for so if you have the sum of them, you have n, the degree to have n -1, right? Because you have each of them. It's more like this one is like a Laplacian matrix of the complete bipartite, of the complete graph. Oh my God. Okay, got this back. Yeah, so I is the identity element, and n is just to compensate for the subtraction in the diagonal entries. That's the degree of the of each vertex, right? And with this, then we have a nice arrangement of how to compute the Laplacian spectrum of the complement. So we consider the orthogonal, we know eigenvectors corresponding to the LG, right? As Stefan mentioned earlier on. So we have the spectrum since it's symmetric, which has orthogonal eigenvectors. And the more interesting aspect is that the all ones is always an eigenvector and correspond to the eigenvalue 0 here. So we will take advantage of that and use it here. So we know that for eigenvalue 0, we have that the all ones is an eigenvector, right? So let's see whether it's also an eigenvector. So if you have this aspect, so from this here, we can write L of G to be equal to N, and take this to the other side, right? So that's what we have here. Then checking whether the all one is an eigenvector. So we have this one to give the 0 here. This to the all n, this is all one, so we have the n minus 1, and this will give us that. So the n minus n will give 0, they'll give us 0 as the eigen. So you can see that 0 is also in the spectrum of its complement. To find the others, since all these eigenvectors to go now, then we know that all the other eigenvectors, if they exist, should be also orthogonal to the all one matrix, right? What happens? Okay. Okay, thank you. Hey, I think there's something wrong. Okay, fine. Yeah. Yeah. So if you let these eigenvectors corresponding to the eigenvalues of the L of G, then we can actually use this idea to compute here. So because they are orthogonal to the all ones one, that's why this side becomes 0. And from here we get the to in, and this side to be the I. So definitely we get our results, right? So that gives us the spectrum of the complement of the graph. And the question is, what can we use this information? Yeah. So if you consider the complete bipartite graph, we can think of it as the union, right? The complement of the disjoint union of complete graphs. For example, so if you have K2 here, and you have K3 here, if you take the union of this and its complement, we get up to this one. Because if you take the complement of this, it forms an edge here, and this one forms connected to everyone there. So we get two complete graphs, and their union gives us that. We know the spectrum of complete graphs, and that's from Stefan's lecture. And we know the disjoint union, how to find this joint union. So we have every tool now to use to find the spectrum or the Laplacian spectrum of Kn, right? So that's the other method I will use. So there we are taking advantage of the operation, and we apply the problem too. So this is just a recall. So if it's the Laplacian spectrum of the complete graph, this is a complete graph, is n minus one, n with n minus one multiplicity, and that's 0, right? So with this, we can easily now prove for the case of this. So if I consider m, n, right? So this km here has this eigenvalue. So m occurs what? M minus 1 times. And n also occurs what? N minus 1 times. So they are in the spectrum here. So the disjoint union, the spectrum. Now, if we consider this as equal to that, then applying our theorem, then we know that this will be equal to, now our n is now m plus n. That's the total number of edges and the total number of vertices. So minus the 0 here, minus that. And you see that this side will take away all the m here. So we have this n here is now m minus 1 times, and this is also n minus 1 times. And that gives us our results as stated earlier. So basically, the two methods can be all used to explain or to help derive some of these the spectrum. It's not always that easier for this spectrum to be obtained. So we can also think about this operation. One problem which I could also maybe ask, or you can think about it later, can we maybe, from this idea, there are some graphs, for example, the path of length 4. If you take the complement of it, it's still the path of length 4. Do we find a way of characterizing such self-complement graphs? Does it follow from these ideas? So these are some questions which we can, or it's a natural questions which we can ask from studying this method. And some of these graphs are very difficult to compute in the classes of graphs. So with this graph operation, Stefan mentioned a few, join, the cross product, and other operations can also be used to find the spectrum. So the next thing is focus on the spectral radius, right? So our third problem talks about, so this more like a characterization of, I think if the spectrum has the spectral radius rather than negative, this one. So if the spectrum is symmetric about 0, spectral will prove that is then if it's bipartite, then the spectrum is um, symmetric about 0. So if lambda is an eigenvalue, then minus lambda is an eigenvalue. So is the spectral. But this is the other way around. If you have if we only know that the spectral radius negative of the spectral radius is in the spectrum, then we could conclude that it is a bipartite graph. To prove this idea, we will consider the spectrum, the eigenvalues, sorry, the eigenvectors, right? So if we let this vector to be the eigenvector of this, because we have that condition, we are saying that this one is in the spectrum of G. So there is an eigenvector corresponding to this, right? This is not the actual, it is just like a notation. So let's not the actual good notation, but we will just to emphasize. That's why I gave this one. So there's like the point-wise absolute value of the entries of S, right? Or what? Absolute value of X, the entries of S. That's what I define as this, right? Then if you compute this, I think it's easy to see that this is equal to that. And since this is the eigenvalue, we have this. And by the triangular inequality, that's the component-wise, we have this inequality, right? And since the entries of here is all positive, and by the formula theorem, then this necessarily will be an eigenvector and corresponding to the lambda, which is the eigenvalue. And if such as this, then it should be an equality, not a less than, right? Because if you have all positive and it has this working with it, then is the eigenvalue. Okay. So with this idea, then we say that the entries of this has no 0 in it, right? So it has either positive or negative values. And with that idea, then we can now split the vertex sets into two, where we can make it P and N, where if your corresponding entry in S is positive, then you are in P. And if it's not positive, it's negative, you are in N, right? And now we can now consider this relation here. And this relation will also make sense if only if the edges or the edges formed in the graph are from the set P to the N. And there's no cancellation because you have here to be negative here. You need from one set to for this to coincide with, because remember the entries here are all positive, right? So for this to coincide and work well, or for no cancellation, then we should have that. And this construction describes what a bipartite set, a bipartite graph. So with this idea, we have that if you have that row inside the spectrum, then we can now be negative row inside the spectrum, then we can have the graph to be bipartite. So there's more like a nice classification or nice way of thinking about these graphs, right? By using the spectrum, yeah. So another interesting problem is about the subgraph, and it's all about the spectral radius. We are still talking about the spectral radius. So if we remove, this problem states that if we remove a vertex or an edge from a graph, right, to get maybe a subgraph, or yeah, then it turns out that the spectrum reduces, right? It's the spectral radius rather reduces or decreases, and this side becomes more straight if G is connected, right? Yeah. So here we make it into general, like in general, it could be a disjoint union. So, but when everything is connected, then we have a straight inequality. Um, so let's think about a proof of this. Um, to prove this one, we consider H if you remove a vertex. So let's prove the first case, taking out a vertex, right? If you take out a vertex, then the vertex set has reduced, right? So if you let this vector be an eigenvector, be its Perron vector, or the eigenvector corresponding to the spectral radius of the smaller graph, right? And we know that all these entries are non-negative, right? Because of the Perron formula theorem. This time not positive because we are not concerned about everything being connected. When everything is connected, then we can now talk about positivity here. But so non-negative here. And if you define another vector, a new vector that's S prime by introducing a new entry, right? Now we have like n plus one entries here. And this x naught corresponds to the vertex that was deleted from G, right, to get H. And if you set that entry to be zero, it's not difficult to check about. So there's a relay quotient, right, or respect to S, and S prime is equal to that because it just basically takes the row that corresponds to the deleted vertex and change it to zero. So this one coincides very nicely. Now with this idea, it's easy to show that we know from the relay quotient definition. So have this one, since this is not the spectral radius, it's not the Perron vector, it's not the eigenvector corresponding to this spectral radius. We have it to be greater than that because it coincides with this one. We have that, and there we get our first proof. For the case when we remove an edge, right? We can take this x as entry as a eigenvector corresponding to row of H, right? And since now they all have the same, deleting an edge not necessarily reduces the number of vertices, so the end will be the same, right? So that fact, and you have A of G, and with it, you know, because you've reduced an edge, right? So there's a missing one in place. So A of G has entries y is greater than that of the A of H, right? So with this idea, and since all the entries of this one not necessarily, since this one is not the spectral radius of G, we have that relation quickly, which is more easier to see. Yeah. But for the case when this is connected, the equality does not hold. Why? Because this will imply that this one is, for the case of the first, this S1, the one we chose here, is also the eigenvector for this, for the spectral radius. But the Perron-Frobenius theorem tells us the entries must be positive, and this one was said to be zero. So that gives us a contradiction. And I leave the second aspect. So you have the same idea, and we can also use to say show that when it's connected with an edge, um, Okay, it's back now. When you remove an edge, this result also holds by this same assumption, right? So we can use the same ideas here to prove that one. Now let's talk about some bounds, right? On the spectral radius. So earlier on, Stefan proved, they proved that the spectral radius is bounded above, by the maximum degree. This is a lower bound, and the proof of this one is not difficult. Let's go through it. So basically, if we take graph G here, right, and let V be the vertex in G, which has a maximum degree, right? Then you obtain a subgraph H from G by just deleting all vertices which are not neighbors of G, of V. If you delete all of them, then you are left with the vertex V and its neighbors. And basically, that's the description for a star graph, right? So the H you get here is a star graph, right? Or it's a complete bipartite graph with one vertex on the other side and the maximum degree, that's the neighbors also on the other side, right? So that's, and we already know how to find the spectral radius of that, right? Because we know the spectrum of the complete bipartite. We know it contains zeros and the square root of m times n. And this time is 1 times the maximum degree, delta. So we have delta here, and that's the spectral radius of that, and that's given by that, and that easily gives us this result. So basically, we can employ this method and try to help solve these problems. Bounds. So there are several bounds. These are we have bounds in terms of the character and in terms of the number of edges, chromatic number, and so many things. So these are one interesting place bound, and also this is also picked from the book as an exercise in the book from Stefan. Yeah. Now let's tackle the last and interesting problem also. Basically, this problem is more like the extremal graphs, and if anyone have worked with Stefan, will know that his favorite for class of graphs are trees. So I cannot leave here. You cannot have a problem session without talking about trees in generality. So we talk about trees now here. So this problem is focused on trees. So there is an operation called a generalized tree shift. And I think Stefan had a brief introduction to that. And this generalized tree shift gives a process structure to all trees of order n. And it turns out that the path and the star are the unique minimum and maximum elements. And with this idea, we can actually show that the spectral radius has a maximum or the minimum. The minimum and maximum spectral radius is the path or the star. Yeah. So I will not go through most of the proof. I'll just give a sketch of the proof and also introduce to some of the properties of these generalized tree shapes. So basically that's it here. So if you take as a path, right? And then we refer to these vertices, these vertices as one is a candidate and one is the beneficiary, right? So from this case, the one going to benefit from the neighbor is the one. For this case, we have V1 going to benefit from the neighborhood from this. So I delete all the neighbors of VK, right, and attach them to V1 here, right, and I get this structure here. One thing to notice here is that when I do that, VK, which was initially not a leaf, becomes a leaf, right? And so this one is called a candidate. We would normally refer to this one as what the beneficiary, the one who benefits from it. And so one important fact is that when this operation is done, so I got T1 from T, it always introduces a new leaf into the new graph. So based on that, we can use that concept to think about ordering all these all trees of a fixed n based on the number of leaves, and that's where the process comes into play. So this is a plenty slide. Yeah? So if from this, we recall this, and I've mentioned that, we observe that the candidate becomes a leaf, that the operation increases the number of leaves from the new tree. So it is important also to realize that this one rather induce a process on a set of trees just of the same number of leaves by ordering the trees according to the number of leaves. So basically, if you have higher number of leaves, that means you had an image of one of the tree with lower number of leaves. So that's the idea. So if T1 is obtained from T, then we know that the number of leaves in T1 is greater than that of what? T. So now based on this fact, we can easily see that the path is not an image of any tree because the path has basically have two leaves, right? And for it to be an image, then means that it came from a tree with one leaf, and the only tree with one leaf will basically be the one node tree. But if you have fixed the number of an n greater than 2, basically you see that is the only tree that's not an image of any of them. So that makes it to be the minimum element in the process there. And also, we can also say that the star is a unique maximum because if I take the star, I cannot produce, but the star always have the largest number of leaves, and I cannot produce a more larger number of leaves, which take when the tree is still connected and is a unique one up there. So that makes it also happen the unique one, and all other trees falls in between the process here. Yeah. So basically, so for example, if you consider the trees of order 6, we can easily see that. So we can always get, so this at level 1 has the part here, it has 2 leaves. And with the part, we can get these 2 graphs here by the GTS. And this one have 3 leaves. And this also induce, so this one can also induce something like that, and this induce that. And you have those with 3 leaves. And now we end up with one with 4 leaves. 5 leaves right now. So you see that the star is a unique one up there, and the part is also the unique one down there here. And what is interesting about this process? So if you have a graph parameter which you are investigating, right? And then you find out that under the operation of the GTS, it increases, right? Then we got a nice result, right? Because it helps us to tell us, it gives the information that the path has the least of that correspond to that parameter, and the star has the highest. I think the converse is also true. When it's decreasing, then you have this one to be the least and this one to be what? The highest, right? So based on this idea, that's what we use to tackle the second part of the of the problem. And we can actually show that if T is obtained, T1 is obtained from T, and if you let S be the parent vector of T, right, then we can use the Rayleigh quotient. We can show that the Rayleigh quotient of T1 with this parent vector is less than that of the, it is greater than that of T with that aspect. So we find out that the spectrum, which is also greater than that, is also, and this is equal to the spectral radius here. And we found out that, so we can actually see that the spectral radius is increasing along the process. And with this idea, we can easily conclude that the path and the star has the maximum and the minimum right and spectral radius. With this same idea, we can also use to compute about the strata index. So in the paper by about the process of these trees, so there's a nice paper by the process of these trees, and there's a couple of results which have been used using just considering this process and able to use to prove these extrema trees. Yeah, but one disadvantage of this problem is like, or not disadvantage or limitation, we cannot say much about all, for example, all those trees on the same level, right? We know that if you came from this side, then we know that you have higher, lower parameter. But what if they are the same level, right? There are other methods which people we employ, something like the measurization approach, where we consider the degree sequence of these graphs, and it also gives us these extremal problems. So there are several tools where we can use to answer some of these questions relating to these extremal problems. Yeah. So basically, so we've talked about the spectrum, how we got the spectrum. We can have several tools, any method, we can use it to get some. There are other bounds, way of bounding this spectrum. We talk about the spectral radius and most other problems. So they can think about so many other problems regarding these other, and there's a whole lot of research on these extrema trees. And so I will say thank you for attention, and I just leave with a quote by D.H. Hardy, and said, "Beauty is the first test, and there's no permanent place for ugly mathematics." So thank you for allowing us to present our beautiful mathematics, and thank you everyone for your attention.
Thank you so much, Dr. Dadedzi, for all this nice, this interestingly nice talk. Okay, any questions?
Hi, hello, yeah, can you hear me?
Now we can hear you, sir.
Okay, thank you. All right, hi, Stephen and Ken. Yeah, so this is sort of a general problem to both Stephen and Ken. So in the case of infinite graphs, we cannot sort of attach matrices to them, sort of. But I guess there are some kinds of operators that could be attached to infinite graphs whose spectra we could study. So sort of just as a general question, are there, do analogs of the problems you've considered here sort of carry over in that setting of infinite graphs, or like, how far can we sort of push these analogies to infinite graphs? I don't know if the question makes sense.
No, it does. It does. There is quite a bit about spectral theory of infinite graphs. What you normally want is that your graphs are at least locally finite. So you don't want vertices of infinite degree, because that tends to mess up things. But infinite locally finite graphs work relatively well. Certain tools carry over nicely. Certain others you have to be careful. So, for example, we used the Perron-Frobenius theorem for non-negative matrices. And it turns out that the analog of the Perron-Frobenius theorem for infinite operators is wrong. So it doesn't work anymore. They're simply counterexamples. So one has to be careful and sort of adapt and at times introduce additional restrictions. But yes, there is quite a lot of theory around the spectra of infinite graphs as well.
Okay, all right, yeah, thanks.
Thank you so much. Thanks for the answer, Stefan. Any more questions?
Thank you very much, Sonwabile. Now, Sonwabile asked me yesterday or the day before, I can't remember, I'm old, just to make some closing remarks. And I had no choice other to say yes. And I'll tell you the reason why. First of all, I really would like to congratulate Sonwabile on having organized this wonderful informative session. I attended maybe 60 or 70% of the lectures. I think I missed the ones yesterday because I had to attend to some other issues. And I would say that one of the reasons amongst many that he approached me to say a few words and also give me the opportunity maybe to advertise a little bit about some of the things that we're doing. It's not the fact that he and I speak the same language and come from within a radius of about 200 kilometers. I've known him even before he finished his PhD at UJ, having been appointed as what we call an N-gap lecturer. Now, I served, amongst other things, on the board of the National Research Foundation. And during my time on the board, we grappled with the question of what makes for a successful research mathematician, especially in the context of the South African science system or the South African university system. And one of the things we picked up is that a number of the people who have been outstanding, and the yardstick here would be the National Research Foundation rating system, is people who have had exposure outside of their university within the South African university system, and also people who have had international exposure. And for some universities in South Africa who are small and cannot afford to provide young academics with an opportunity to spend some time at Uppsala, to spend some time at Oxford, to spend some time at University of Ghana, University of Nairobi, and so on. It's going to be very difficult. And also, I think in the last 2 years, the pandemic that has restricted travel, international travel outside of our country, is such that young people will not have that opportunity. Now, I come from a generation, I'm South African, I live in Johannesburg, where as Black South Africans, we were stripped of our citizenship, and therefore some of us were not even issued with a passport to travel elsewhere. To the extent that when I went to Oxford to do my PhD, I had to get a piece of paper which allowed me to enter the UK. So we have set up a program called Pathways to a Successful Academic Career. And because I'm retired, very little to do, I volunteered to be the coordinator of this year-long program. It's open to young academics who either finished their PhDs in the last 5 years or will be finishing their PhD in the next 12 months. So Sonwabile is one of the people in this group that I've been working with since the beginning of the year. And one of the requirements for the program is that the participants, either singly or as a group, will organize an online event whose aim is really to showcase their work, either by doing the presentation or inviting high-profile people like the ones who gave presentations over the last four days. And also, hopefully, to build the research communities amongst young people. And really, on behalf of our network, which is called the National Graduate Academy for Mathematical and Statistical Sciences, which complements, or its role is complementary to that of the Center of Excellence for Mathematical and Statistical Sciences. I'd like to thank all the presenters for agreeing, being approached by a young person who's just finished his PhD. Maybe some of you have not actually met him in person. He's a wonderful, wonderful, cheerful, charismatic young man. I'd like to thank you for saying yes and availing yourself to give these insightful lectures. I'm not a graph theorist. In a previous life, I was a group theorist. In fact, in my first year at Oxford, I took a course with Professor Peter Cameron on, I think, permutation groups. I can't remember, that was more than 40 years ago. And I would really like to thank Professor Cameron, Professor Ian Moffat, my former colleague in the School of Mathematics at University of the Witwatersrand, Professor Eunice Mpako Banda, and somebody that I met some years ago when he worked for the University of Natal, Professor Peter Dangelman, and I've come across the name of Professor David Ewing, but I don't think he and I have actually met. And of course, I've come across some of the students, I mean, online, your former students from Madagascar, and so on. And we were really grateful for the work that you have done and that you continue to do. And last but not least, Dr. Kenneth Dadedzi from University of Ghana. It's the first time that I meet him online. And really a big thank you to you all, and that this is the beginning of an ongoing engagement to create communities of researchers, of early career academics. Because as I pointed out earlier, it becomes difficult for somebody starting out to make those connections, to set up collaborations. And one of the things that we are aiming to do is to facilitate those connections between our young academics in mathematics and statistics and data science. And through platforms like these, and one of the things that we'll be doing is to support a few of them, about 20, in partnership with the local organizing committee of the International Congress of Mathematicians, to attend the ICM, International Congress of Mathematicians in Russia in 2022. You'll agree with me, those that have been to an ICM, that it's an uplifting experience to be exposed to a whole range of areas of mathematics that one might not have been exposed to, because mathematics is such a broad discipline. There will be, I hope, that you will continue organizing this. And one of my responsibilities is to try to raise funds to be able to support activities like this and to support young academics who are starting out with their careers. With those few words, again, just to close and say that, well done, Sonwabile. I'm very, very proud of you. I really am. Thank you very much to everyone.